So first step, how to find the cluster dimensions. So that is the first part here in the procedure. So for each medoid, and now it's getting really heuristic, as you see. So for each medoid, we define 2 times delta to be the distance to its closest medoid. Yeah. So we have one medoid, and we have so here we have one medoid M, and we have here the closest medoid to M1, which is M2 here, and delta is exactly half the way from M1 to M2. Yeah, so 2 times delta is the distance from M1 to M2, meaning that delta, the delta here, is exactly halfway from M1 to M2. Yeah, so delta is specific to M1, specific to M2, specific to M3, and so on and so on and so on. Now we define all the data points within delta around M1 is the so-called locality of M1, and all those points in locality of M1 will be probably, surely, likely, mostly likely, surely in that case, assigned to this M, yeah, because they are closer to M1 than to any other medoid. Yeah, so that is fine. Yeah. Okay, so now to each medoid, intuitively we want to associate those dimensions where the points are close to the medoid in that dimension. Yeah, so we compute the average distance along each dimension J from points in the locality of Mi, which is denoted as Xij. Yeah, so I is the corresponding medoid. Yeah. And J are the dimensions of our data space. So J goes from 1 to D if we have D features, and I goes from 1 to K because we have K medoids. Yeah. So that is those are the distances, yeah, of points, the average distances of all the points in the locality. Yeah. So here is the locality. Yeah. So all these points here, these 4 points are in the locality of M1, and now the average distance of all these 4 points to M1, but only in all one-dimensional features, that is Xij. Yeah? So for the first attribute, maybe this one here, the x-axis is the first attribute. So we just compute the distance of this one to M1, which is just this one here, yeah, and this one is just here, and this one, and from here to here, yeah, so this one here, and average this. That would be the first entry here in this kind of vector. And for the second feature, we do the same actually, and we do that for all medoids based on all the corresponding localities of the medoids. Then we do a different thing or another thing. For each medoid, the mean and the standard deviation of x1 is calculated. The mean is y, and the standard deviation is sigma. Yeah? And then we calculate this set score here, which is not really a name on its own, but it's just denoted as set, yeah, which is actually the error of, or the difference between the actual average distance from the expected average distance times the standard deviation. Yeah? So, and that is actually the classical statistical normalization. So we take the feature that we have, so the distances that we have, normalize it by subtracting the mean. So the mean is the mean of these distances here, of this distance vector, or this distance matrix actually, is transformed or put into 0, yeah, by subtracting the mean actually, and then divided by the standard deviation, giving that set has a mean of 0 and a standard deviation of 1. Yeah, so that is the basic normalization here. Yeah, and then we take k times L smallest values from these Zij entries with at least 2 features for each medoid, yeah, to ensure that the cluster preferences are low dimensional. So we have different features here now, and we take k times L features, the smallest features. L is this input parameter. Now it's small l, sorry, it should be capital L here, of course. So that is the input parameter. So we choose k times L features, the smallest features from this matrix here, so that we get for k medoids on average L features to be relevant. And we also ensure that each feature has at least 2 dimensions. So the average dimension will be L, the minimum dimension will be 2, and of course the maximum dimension could be D, but that is probably not the case, but anyway. So the output will be a set of medoids and their associated dimensions, which is drawn here from this matrix here. Okay, and once again, this matrix models the best features in the localities of these of all the medoids here. And once again, we normalize that so that we can compare the features among each other. Now that we have assigned for each medoid the relevant features, we can now assign each point to the closest medoid, and we use the so-called Manhattan segmental distance for that. So only the relevant dimensions count, which is, well, Manhattan segmental distance is Manhattan distance, but only the relevant dimensions count. And the relevant dimensions have been determined here in the first step, and now we take these relevant dimensions and compute the Manhattan distance in that case. So Manhattan segmental distance for any 2 points, x1, x2, one will be a medoid, one will be a data point, and any set of relevant dimensions will just take the difference in the corresponding features of these two points here, but only in the relevant dimensions, normalized by the number of dimensions, so that we somehow can compare distances in some 10-dimensional feature space or in some 2-dimensional feature space and stuff like that. So D is the set of dimensions, can be different for different medoids, of course, and so that we get comparable distances for the assignment of points, we normalize the Manhattan distance by the number of dimensions that we used in the computation. Then we evaluate a cluster using the average Manhattan segmental distance from the points in C to the centroid of this of this cluster I, along each dimension J, of course, each relevant dimension J. So also the optimization function, the cost function, not uses the distance. The distance in the entire feature space, but the Manhattan segmental distance, which makes sense, of course. So once again, if one of them, the medoids have 4-dimensional subspace preference, for example, so only 4 dimensions out of, say, 10 are relevant, then it would be a sum of 4 different features, differences in 4 different features divided by 4, and also the compactness of the cluster will only be computed in this 4-dimensional subspace, of course. Okay. Then replace bad medoids with random points from M is the classical way as we do it in k-medoids clustering. And of course also the termination is the same as before, or as in traditional clustering algorithms or traditional k-medoid clustering algorithms, if the clustering quality does not increase after a given number of current medoids have been changed or exchanged with new medoids from M. And it's it's not clear if there is another hidden parameter in this criterion, because that somehow asks for how many should we use actually, or does the quality have to increase or decrease more than a given threshold and stuff like that. So from the paper, if you read it, it's not too clear if there is another parameter determines or defines this specific stop criterion actually. Yeah, but that's a different point. Yeah, and then there will be a third phase. So that is the cluster assignment and actually feature relevance search. Yeah, so that is the iteratively refinement of cluster memberships and cluster subspaces. And the third phase is again something different, which is a refinement here in that case. So we reassign subspaces to medoids as above with this procedure here, but now we only use those points assigned to each cluster rather than the locality of each cluster. Yeah? So in the last point, only in the last point, so the locality, so that is the locality assumption here. The locality is computed in the entire feature space. Yeah? And only in the very, very last step, when we are almost done, we again compute the locality, but now based on the relevant features of each medoid. Yeah? So in all the other steps, we always compute the locality based on the entire feature space, and based on the locality, we compute the relevant features. Yeah? And that is this locality assumption that the neighborhood of cluster memberships in the entire feature space somehow is sufficient to determine the subspace preference of clusters. Yeah? So we do that in the last phase now in probably in a suitable way. Then reassign points to medoids, and points that are not in the locality of any medoids are then classified as noise. Yeah. So you see here that this locality is the key concept for learning, but for learning the features, but also in the last phase for deciding about outliers and noise points.